Hey there, dreamers. Welcome to Hafee Sleep. Whether you're tuning in from a bustling city where the lights never quite dim, or a quiet town where the stars are still visible, whether you're winding down for the night or it's the middle of the day and you just need a moment of cosmic calm, I'm so glad you're here. Tonight, we're going on a journey unlike any other. We're going to ask a question that has haunted poets, scientists, and stargazers for millennia. Could we ever truly leave our galactic home? Could we venture beyond the Milky Way? It's a story of impossible distances, incredible technology, and the boundless human spirit. So, get comfortable, let your mind drift, and together, let's wander the cosmos. If this journey captures your imagination, if it helps you relax and drift into a deeper wonder, then please do consider subscribing to Hafee Sleep. It's the easiest way to make sure you never miss our next adventure into the unknown. And I'd love to hear from you in the comments below. Tell me where in the world you're listening from and what time it is for you. It's always amazing to see our community of cosmic dreamers spanning the globe. Now, let's begin. Have you ever, on a perfectly clear, moonless night, far from the glow of city lights, looked up? I mean, really looked up. Not just a glance, but a long, deep, soul-searching gaze into that vast, star-strewn blackness? If you have, you've seen it. A faint, milky, ethereal river of light arching across the heavens. The ancient Greeks saw it and told a story of spilled milk from the goddess Hera. We know it as something far grander, our home, the Milky Way galaxy. It's not just a smear of light. It's a colossal pinwheel of gas, dust, and over 100 billion stars, one of which is our sun, a rather average star on a quiet suburban street called the Orion Spur. We are, all of us, every person you've ever known, every mountain, every ocean, every whispered secret and roaring triumph aboard a spaceship called Earth, orbiting that sun, which is itself hurtling around the galactic center at hundreds of thousands of kilometers per hour. We are already cosmic travelers, but it begs a question, a thrilling, terrifying, profoundly human question. Can we, the inhabitants of this tiny pale blue dot, ever leave our galactic home? Can we step out from the Milky Way and into the intergalactic void? The short, honest answer, with our current understanding of physics and technology, is a resounding, overwhelming, almost laughable no. It is the most formidable challenge imaginable, a leap that makes climbing Mount Everest look like stepping over a crack in the pavement. But, and this is a very important but, the human spirit is not fed by short answers. It is fueled by the what if, the how could we, the audacious act of staring into the face of impossibility and asking, well, why not? So let's embark on a journey of our own, a thought experiment of epic proportions. Let's pack our imaginary bags with curiosity, leave our doubts on the launch pad, and explore the mind-bending possibilities, the terrifying obstacles, and the far future dreams of what it might take to truly leave the galaxy. First, we need to understand what we're up against. We need to grasp the sheer, staggering scale of our home. We often hear the numbers, but they wash over us. They are too big to feel. Let's try to make them feel real. Imagine our entire planet, Earth, is shrunk down to the size of a single grain of sand, a tiny, almost invisible speck. On this scale, how big is the moon? It's another, slightly smaller grain of sand about 3 centimeters away. Not too bad. And the sun? On our grain of sand Earth, the sun would be a large beach ball, about the size of a big exercise ball, located. Are you ready for this? over 100 meters away. That's the length of a soccer field. Our entire solar system, out to the orbit of Neptune, would span about 6 kilometers. You'd need to drive to really see its full extent. Now, hold on to your hat. On this same scale, where Earth is a grain of sand and the solar system is 6 kilometers across, the next nearest star system, Alpha Centauri, would be over 16,000 kilometers away. That's roughly the distance from New York to Sydney, Australia. All that emptiness, just to get to the next few grains of sand. And the Milky Way? This entire galaxy, containing over 100 billion of those star suns, would be, are you sitting down? About 100 million kilometers across. That's more than the actual distance from the real Earth to the real Sun. Our entire grain of sand solar system is lost, utterly and completely lost, in a volume of space so immense it defies all human intuition. So, we've established that the first and greatest wall we hit is distance. It's a word we use every day without really feeling its weight. We talk about the distance to the grocery store, the distance to the office, the distance across the country. These are distances we can comprehend. We've driven them, flown them. We have a physical, gut-level understanding of what it means to traverse them. But the distances we're talking about now, the cosmic distances between stars and across galaxies, are of an entirely different breed. They belong to a category of scale that the human brain did not evolve to understand. Our instincts, our intuition, are completely useless here. They break down. They short-circuit. To truly grasp it, we have to perform a kind of mental judo, using metaphors and comparisons to force our earthbound minds to comprehend the heavens. Think of it like this. Imagine you're standing on a vast, perfectly flat desert that stretches out to the horizon in every direction. This desert is the emptiness of space. Now, in this entire desert, there are only a few dozen grains of sand. That's it. Just a few dozen. Each one of those grains of sand is a star. Our sun is one of them. The nearest grain of sand, our nearest stellar neighbor, Proxima Centauri, isn't a few feet away. It isn't a few yards away. On the scale of this imaginary desert, the very next grain of sand is over 40 miles away. 40 miles of absolutely nothing but flat, empty desert to get to the next tiny speck. That's the local density of our stellar neighborhood. That is the emptiness we have to cross. And how are we planning to cross it? With our current technology, it's as if we've built a little toy car, wound it up, and pointed it in the direction of that grain of sand 40 miles away. That toy car is our Voyager 1 probe. It is, without a doubt, a masterpiece of human engineering. It carries a golden record with greetings from Earth, sounds of our planet, music from our cultures, a message in a bottle hurled into the cosmic ocean. And it is moving. It's zipping along at a truly impressive 38,000 miles per hour relative to the sun. To us, that speed is phenomenal. It's over 10 times faster than a speeding bullet. If it could fly at that speed in our atmosphere, it could go from New York to Los Angeles in about 4 minutes. But out here, in our desert analogy, that blistering, unbelievable speed translates to something pathetic. Something laughably slow. If our toy car is moving at Voyager's speed on this scale, it would be inching forward at a pace so slow you couldn't even see it move with your naked eye. You'd have to stare at it for hours to notice it had budged a millimeter. At this pace, the journey to that next grain of sand 40 miles away would take not years, not decades, but tens of thousands of years. This isn't a journey, it's a geological process. It's like planting a sequoia tree whose seedlings your species' distant, evolved descendants might one day sit under. It's a time scale that dwarfs human history. Let's put a finer point on that 70,000-year figure for Voyager to reach Alpha Centauri. 70,000 years ago, what was happening on Earth? The world was a very different place. It was the peak of the last ice age. Vast sheets of ice, thousands of feet thick, covered much of North America and Europe. Neanderthals still walked the earth, sharing the landscape with early Homo sapiens. The first cave paintings were perhaps just being conceived in the minds of our ancestors. If someone had launched Voyager back then, as the glaciers were at their maximum extent, it would only just now, in our lifetime, be arriving at its destination. All of recorded human history, the rise and fall of empires, the invention of writing, the agricultural and industrial revolutions, the digital age, all of it would have fit comfortably into the travel time of this, our fastest object. This is what we're up against. This is the reality of the cosmic distance scale. It's a reality that doesn't just laugh at our ambitions. It doesn't even notice them. It's completely indifferent. The universe is not designed for convenience. It wasn't laid out with our travel plans in mind. The sheer yawning emptiness is the default setting of the cosmos. Matter, the stuff that makes up stars, planets, and us, is the rare exception. The void is the rule. This emptiness, this incredible nothingness between stars, is called the interstellar medium. But it's a bit of a misnomer because it makes it sound like there's something there, like a medium. It's not a true vacuum, but it's so close that it might as well be. In the space between stars, there are, on average, a few atoms in every cubic centimeter. To put that in perspective, the air we're breathing right now has something like 30 quintillion molecules in that same cubic centimeter. A quintillion is a 1 with 18 zeros after it. So space isn't just empty. It's emptier than any vacuum we can create in our most advanced laboratories on Earth. It is the deepest, most profound silence imaginable. Now, imagine our little Voyager probe, this tiny, intricate machine, sailing through this incredible void. It's utterly alone. The light from the sun, from where it is just another bright star in the sky, not the blazing orb we know. It's been traveling for over 40 years, and in all that time, across billions of miles, it has not come close to anything. Not a single atom of its structure has collided with anything substantial from the outside. It's on the most solitary journey any human-made object has ever undertaken. It's a testament to our desire to reach out, to explore, but it also highlights our profound isolation. We are, for all intents and purposes, marooned on an island in a vast and empty sea. This is why the idea of leaving the galaxy is so monumental. It's not like packing up the car and moving to the next state. It's not even like the ancient Polynesians navigating vast stretches of the Pacific Ocean. In those ocean voyages, there was always something. The water, the wind, the currents, the fish, the birds. There was a medium to travel through and signs of life. Interstellar space, and especially intergalactic space, offers none of that. It is the ultimate desert. A voyage to another star is like trying to cross the Pacific Ocean on a raft. But if the Pacific Ocean were drained of all water, all air, and stretched out to be 1,000 times wider, the scale is simply not of this world. This is the fundamental problem that any future starfarer must solve. It's not just about going fast. It's about going fast for a very, very, very long time. It's about building a ship that can not only accelerate to a decent fraction of light speed, but also sustain itself, protect its occupants, and navigate the void for centuries or millennia. The distance is the immutable factor. It is the boss we have to work for. All of our technology, all of our cleverness must be bent to the singular purpose of overcoming this one simple, brutal fact. Space is big, and everything else is very, very far away. So when we talk about building fusion rockets or antimatter drives or light sails, we're not just talking about making a faster engine. We're talking about building a bridge across those 40 miles of empty desert. We're talking about creating a technology that can compress the incomprehensible vastness of time and space into something manageable, into something that fits within the lifespan of a hopeful species. The distance is the wall. Our imagination and our ingenuity are the tools we have to try and climb it. And as we'll see, that climb will require us to rethink not just physics, but the very nature of time itself. So we've established that our current speed is, well, let's be kind and call it leisurely for interstellar travel. It's the pace of a garden snail setting out to cross a continent. If we're ever going to get anywhere interesting before our species evolves into something else entirely, we need to pick up the pace. We need to stop thinking like pedestrians and start thinking like beings who understand the universe's rules. And the universe has a very strict speed limit. It's not posted on any cosmic signpost, but it's woven into the very fabric of reality itself. It's the speed of light, 300,000 kilometers per second. That's so fast that it circles the entire Earth about 7.5 times in a single second. Whoosh, you're around the world. Whoosh, you're around again. It's a speed so profound that it's less a velocity and more a fundamental constant of nature, like the gravitational constant or the charge of an electron. It's the universe's ultimate traffic law, and nothing with mass can ever quite reach it. You can get infinitely close, but you can never hit it. It's the final barrier. Now, let's put our Voyager probe's speed into this new, more realistic perspective. We said it was going 17 kilometers per second, which sounds fast. But compared to light speed, it's moving at a paltry 0.0056% of the cosmic speed limit. If the speed limit is 100, Voyager is doing 0.0056. It's not even crawling. It's essentially motionless on this new scale. It's like a single-celled amoeba trying to cross the Atlantic Ocean by doing the breaststroke. The commitment is admirable, but the timeline is absurd. So, what's a reasonable goal? What's a speed that's still fantastically, mind-bogglingly fast, but doesn't require us to break physics as we know it? Let's dream big, but practically. Let's aim for 10% of light speed. 10%? That's 30,000 kilometers per second. Let's try to make that number feel real. Imagine you're standing on the surface of the Earth, and you have a spacecraft that can instantly accelerate to this speed. You fire the engines. In the first second, you're already 30,000 kilometers away. You've instantly left the Earth's atmosphere far behind. In just over a second, you've passed the moon. Think about that for a moment. The Apollo astronauts took 3 days to get to the moon. You'd get there in less time than it takes to sneeze. The moon would be a momentary blur outside your window. Mars? At its closest approach to Earth, it would be a 2-day trip. Not bad. You could pop over to the red planet for a weekend excursion. The outer planets? Jupiter, which is over 600 million kilometers away, would be reachable in about 3.5 hours. Saturn in 7. The entire solar system, our entire cosmic backyard, suddenly becomes a local neighborhood. It shrinks. The distances that felt immense with chemical rockets become trivial. You could have a meeting around Saturn's rings and be home for dinner. This is the transformative power of speed. It literally changes your perception of the universe. It makes the vast seem intimate. But we're not just talking about touring the solar system. We're talking about leaving it. Our real goal is Alpha Centauri, that next grain of sand in our cosmic desert, 437 light-years away. At 10% of light speed, the math suddenly starts to become almost human. A light-year is the distance light travels in 1 year. So, if you're going 1/10 that speed, it will take you 10 years to travel 1 light-year. For a 4.37 light-year journey, you're looking at a travel time of about 44 years. 44 years. Now that is a number we can wrap our heads around. It's a long time, certainly. It's most of a working career. It's more than half an average human lifespan. But it's not 70,000 years. It's not a geological epoch. It's a time frame that fits within the scope of a single human life. This changes everything. It moves the mission from the realm of pure fantasy into the realm of the theoretically possible. It's a staggering engineering challenge, make no mistake, but it's no longer a violation of physics. A person could, in theory, be born on Earth, trained to be an astronaut, spend 44 years in flight, and arrive at Alpha Centauri in their old age. Or more likely, a young, carefully selected crew could be sent on a one-way mission of colonization. They would say goodbye to everyone they ever knew, to the entire Earth, forever, knowing they would live out their lives on the ship and their children would be the first to see the new sun rise over a new world. This is the concept of a generation ship, a vessel that is not just a ship, but a sealed world, a self-contained ecosystem hurtling through the void. It would have to be enormous, a floating city with farms, schools, water and air recycling systems, and a stable society capable of maintaining itself for decades without any hope of resupply or rescue. The social and psychological challenges are as daunting as the engineering ones. Could a community of a few hundred or thousand people remain healthy, sane, and purpose-driven for 44 years in the absolute blackness of interstellar space, with nothing outside their windows but the unmoving pinpricks of stars? They would be the most isolated humans in history, a tiny bubble of life surrounded by an infinite desert. But the 44-year timeline is also a bit of a trick, a simplification. It's the time from the perspective of us, the people left on Earth. We would watch the ship launch, and then we would wait, and wait. And 44 years later, we would get the signal that they had arrived. But for the crew on the ship, thanks to Einstein's special theory of relativity, time would actually be passing slightly more slowly. The faster you move through space, the slower you move through time relative to someone who is stationary. This isn't science fiction. It's a proven fact, confirmed by incredibly precise atomic clocks on airplanes and satellites. At 10% of light speed, this time dilation effect is very small, but it's there. For every 44 years that pass on Earth, about 43.8 years would pass on the ship. The crew would age about 3 months less than everyone back home. It's a tiny difference at this speed, but it's a hint of the strange time-warping effects that become dramatic as you go faster. It means that if we could go even faster, say 90% of light speed, the trip time from the crew's perspective could be cut down dramatically. A 44-year journey could feel like only 20 years to them. This is the other way to attack the problem of distance, not just by moving faster through space, but by bending time itself to make the journey feel shorter for the travelers. So achieving 10% of light speed isn't just about getting there quicker. It's the key that unlocks the door to the stars. It transforms an impossible journey into a monumental but conceivable undertaking. It's the difference between throwing a message in a bottle into the ocean and building a seafaring vessel to cross it. It's the first crucial step away from being prisoners of our solar system and toward becoming citizens of the galaxy. But as we'll soon see, generating that kind of speed requires not just a new engine, but a new way of thinking about energy itself. This is where physics, engineering, and imagination collide. The first and most obvious problem is propulsion. Our chemical rockets, the kind that took us to the moon, are useless for this. They are like trying to sail across the Pacific Ocean in a bathtub. They just don't have the efficiency or the power. We need entirely new ways to push ourselves through space. One of the most discussed and theoretically plausible concepts is nuclear propulsion. Not nuclear bombs, but controlled nuclear reactions. Imagine a reactor, much like on a nuclear submarine or aircraft carrier, but in space. It would heat a propellant, like liquid hydrogen, to tremendous temperatures and then blast it out of a nozzle to create thrust. This is called nuclear thermal propulsion. It could be maybe twice as efficient as our best chemical rockets. A step forward, but still not enough for star travel. So we need to go faster, much faster. We've talked about the need to reach a significant fraction of light speed, and that requires an energy source far beyond our chemical firecrackers. We need to harness a power that's truly stellar in nature. And in the mid-20th century, at the height of the atomic age, a group of the brightest and most daring minds in America asked a very simple, very terrifying question. What if we use the most powerful force we've ever unlocked as a propellant? This isn't about a controlled nuclear reactor, like on a submarine. This is far more direct, far more visceral. This is the concept of nuclear pulse propulsion, and it's exactly as crazy as it sounds. The idea, in its most breathtakingly bold form, is to propel a spacecraft by detonating nuclear bombs behind it. Seriously, you read that right. Not with a reactor, but with bombs. This wasn't just a sketch on a napkin. It was a seriously funded, deeply studied project called Orion, run by General Atomics in the late 1950s and early 1960s. And for a brief, glorious moment, it seemed like it might actually work. Let's unpack how this madness would operate. Imagine your spacecraft. It doesn't look like a sleek, needle-nosed rocket. It looks more like a massive, blunt-ended skyscraper or a colossal upright sewer pipe, because the business end is at the back. This is the pusher plate. It's a giant, circular slab of the toughest material we can imagine, probably a super alloy coated in something like graphite to handle insane heat. It's not just a plate, it's also a shield, because directly behind it is where the magic, or the mayhem, happens. The ship is loaded with thousands of small, specially designed nuclear devices. Think of them as atomic firecrackers. One by one, a mechanism would drop one of these bombs out of a hatch in the center of the pusher plate. It would fall just a short distance, maybe 100 meters or so. And then, bang, it detonates. Now, in the vacuum of space, a nuclear explosion doesn't create a fiery mushroom cloud like on Earth. There's no air to superheat and carry the debris. Instead, it creates an instantaneous expanding sphere of pure incandescent plasma, a sun-like fireball of subatomic particles and radiation moving at a tremendous fraction of light speed. This expanding ball of hellfire slams into the pusher plate. The force of that impact is unimaginable. It's like being hit by a tidal wave made of pure energy. The pusher plate, designed to absorb this stupendous blow, is kicked forward violently, and since the force just vaporize the plate, turn it into molten slag. This is where the genius of the design comes in. The pusher plate isn't bolted directly to the main body of the ship. It's connected by the most heavy-duty shock absorbers ever conceived, a system of enormous pistons and dampeners. So, when the plasma wave hits, the plate itself is driven backward up these pistons, compressing them. The energy of the explosion is thus converted into a controlled mechanical push rather than a destructive shock wave. The plate might get incredibly hot, but it's designed to ablate, to shed its superheated surface layer like a lizard shedding its skin, which also helps to cool it. By the time the plate rebounds from its stroke, ready for the next push, the hot debris has dissipated into space behind it. Now you do this again. Drop, bang, push, and again. Drop, bang, push, and again. Every second or every few seconds, another atomic firecracker goes off. Bang, bang, bang. The ride wouldn't be smooth like a jetliner. It would be a constant, rhythmic, pounding acceleration. Thump, thump, thump. It would be like the world's most powerful jackhammer, firing at a rate that would slowly, inexorably build up speed. From the outside, it would look like a man trying to climb a cliff by repeatedly setting off dynamite in his hands and being blown upward by the blast. It is the absolute definition of brute force, and the calculations showed this brute force method could work astonishingly well. A full-scale Orion ship, a city block-sized behemoth, could theoretically reach speeds of 3, 5, even 10% of the speed of light. It could carry a payload the size of a small town, thousands of people, their supplies, entire ecosystems, making it a generation ship par excellence. The project's proponents dreamed of sending a fleet of these space battleships to Saturn by 1970. They weren't thinking small. But of course there are rather enormous buts. The first and most obvious is the launch. You can't possibly light this thing off from the surface of the Earth. The first few detonations would not only vaporize the launch pad, but would likely create a radioactive firestorm that would poison the atmosphere for miles around. The electromagnetic pulse from the blasts would fry electronics across a continent. The political and environmental nightmare of even testing such a system is unimaginable. The Project Orion team knew this. Their plan was to build the ship in orbit, using conventional rockets to lift the parts. The nuclear bombs would only be set off once they were far away from Earth, in the deep black where the fallout would harm no one. But that leads to the second, more subtle problem: the Partial Test Ban Treaty of 1963. This international agreement, a response to the very real fears of nuclear annihilation during the Cold War, prohibited the testing of nuclear weapons in the atmosphere, underwater, and in outer space. Setting off hundreds of nukes in space, even for peaceful purposes, would be a blatant and terrifying violation of this treaty. It would look to every other nation on Earth like a nuclear attack was underway. The potential for catastrophic misunderstanding was, and still is, far too great. So Project Orion was shelved, not because it was scientifically impossible. The physics, shockingly, is sound, but because it was politically and environmentally untenable. It was a product of its time, born in an era of atomic optimism and Cold War tension, when the power of the atom seemed to be the answer to every problem, even the problem of distance. Yet, the idea retains a certain gritty, compelling charm. It doesn't rely on magical materials or undiscovered physics. It uses a terrifying technology we already possess in a wildly novel way. It's the ultimate expression of, if you can't find a door, just use a cannon. It's the kind of solution a species might turn to if it were desperate, if it absolutely had to leave its solar system quickly and with a lot of baggage. It's not elegant, it's not clean, but it has a raw, honest power to it that more fanciful concepts lack. It's a reminder that sometimes the path to the stars might not be quiet and graceful, but loud, violent, and punctuated by the rhythmic thunder of man-made stars flaring into existence in our wake. Then there's the concept of fusion rockets. If we can ever achieve sustained, controlled fusion, harnessing the power that lights the stars, we could have an incredible energy source. A fusion rocket would work by shooting small pellets of fusion fuel, like deuterium and tritium, into a reaction chamber, igniting them with powerful lasers or magnetic fields, and then channeling the resulting superhot plasma out a magnetic nozzle to create thrust. The exhaust velocity could be a significant fraction of light speed, making the rocket incredibly efficient. Speeds of maybe 10–20% of light speed might be possible. This is one of our best bets for within the next millennium star travel. So we've talked about brute force, about literally throwing nuclear bombs out the back door, and also the clean fusion rockets to push us along. It's a wild, almost punk rock approach to space travel. But what if we could leave all that behind? What if we could move beyond mere explosions and tap into the pure, fundamental energy of creation itself? What if we could find the universe's ultimate battery? Well, according to physics, we already have. It's called antimatter, and it is, without a doubt, the most potent, the most efficient, the most terrifyingly perfect fuel source that reality allows. To understand antimatter, we first have to take a little detour into the heart of what everything is made of. You, me, this planet, the stars, we're all made of matter, the familiar stuff. Atoms with electrons whizzing around a nucleus of protons and neutrons. Now, for every type of matter particle, physics tells us there should be an opposite, a mirror image, a twin born with opposite properties. For the electron, there's the positron, identical in mass, but with a positive charge instead of a negative one. For the proton, there's the antiproton, negative instead of positive. This is antimatter. It's not some magical substance from a story. It's a real, predicted, and observed part of the universe. It's the ultimate example of cosmic symmetry. For every yin, there is a yang. And when this yang meets its yin, when matter and antimatter meet, they don't just react like chemicals. They don't combine or explode in a conventional sense. They perform the ultimate vanishing act. They annihilate each other. Poof. In a flash of energy, they cease to be matter entirely. 100% of their mass is converted into pure energy, according to the most famous equation in the world, EMC square. Let's unpack that for a second, because we throw that equation around a lot without feeling its weight. E is energy. M is mass. C is the speed of light. And the speed of light is a huge number, but c square is that number multiplied by itself. It is an astronomically enormous number. This means that a tiny, tiny amount of mass is equivalent to a colossal, mind-boggling amount of energy. It's the reason the sun can shine for billions of years, fusing a tiny fraction of its mass into energy. But even the sun's fusion process is inefficient. It only converts about 0.7% of the mass involved into energy. Matter-antimatter annihilation is 100% efficient. It is the universe's gold standard for energy production. To give you a sense of scale, let's play with some numbers. The space shuttle's enormous. Rust-colored external fuel tank held over 700,000 kilograms of liquid oxygen and hydrogen. The energy released by burning all that propellant is what lifted the shuttle into orbit. Now, How much antimatter would it take to release the same amount of energy? Are you ready for this? About 10 grams. A single paperclip weighs about a gram. You could hold the equivalent energy of a space shuttle launch in the palm of your hand. A few hundred grams of antimatter could theoretically provide enough energy to send a large crewed ship on a tour of the entire solar system. A few kilograms could be enough for an interstellar journey. This is power on a scale that redefines what's possible. So how would an antimatter rocket work? It wouldn't be about annihilation directly creating thrust. That would be a beam of pure radiation shooting out the back, which is incredibly energetic, but doesn't provide much push in the conventional sense. Instead, the most practical design is what's known as an antimatter-initiated fusion rocket. Imagine a robust reaction chamber at the stern of the ship. Inside, you have a pellet of fusion fuel, like deuterium and helium-3. Then you inject a tiny, precisely metered amount of antimatter, a few billionths of a gram perhaps, into the center of this pellet. The instant the antimatter contacts the matter in the pellet, it annihilates. This isn't a slow burn. It's an instantaneous, microscopic star being born and dying in a nanosecond. The energy released is so intense, so ferociously hot, that it triggers a fusion reaction in the surrounding fuel, just like the heart of a star. This creates a superheated plasma, an ionized gas with temperatures in the millions of degrees. This plasma, now expanding violently, is then channeled and directed out of a magnetic nozzle. Because the plasma is electrically charged, powerful magnets can squeeze it and shoot it out the back like a blowtorch, pushing the ship forward. The antimatter is merely the match. The fusion plasma is the bonfire it lights. The efficiency of this process is off the charts. The exhaust velocity, the speed at which the propellant is flung out the back, could be a significant fraction of light speed itself. Remember the tyranny of the rocket equation? The faster you can throw your exhaust out, the less propellant you need to get a push. With an antimatter-driven exhaust velocity, you could achieve constant, powerful acceleration for months or years, potentially reaching 50, 60, even 90% of light speed. The journey to Alpha Centauri could shrink from millennia to years, from a multi-generational odyssey to a single mission. This is the game changer. This is the technology that could truly open the galaxy. But, and this is a but so massive, it could have its own gravitational field. There are monumental, perhaps even show-stopping, problems. We've been talking about grams of antimatter as if it's something you can just pick up at a cosmic gas station. It is not. First, production. Antimatter is incredibly difficult to make. We currently produce it in particle accelerators, like CERN. They smash particles together at near-light speeds, and in the energy of those collisions, particle-antiparticle pairs are created. We can then use magnetic fields to separate and trap the antimatter. The current rate of production is humble. We measure it in atoms. We might produce a few billion antiprotons in an experiment. A billion antiprotons sound like a lot, but it has a mass of about 1.6 trillionths of a gram. To make a single gram of antimatter, we would need to scale up our current production rate by many, many orders of magnitude. The energy required to produce it, with our current hopelessly inefficient methods, would be staggering. It's been estimated that with today's technology, producing a single gram of antimatter could cost trillions of dollars and consume more energy than a large nation uses in a year. We wouldn't be fueling a starship. We'd be bankrupting planets. Second, storage. This is the real nightmare. Antimatter cannot touch matter, not even a little bit. If a single atom of it touches the wall of its container, it annihilates. So how do you store it? You use a device called a penning trap. It's a miniature, incredibly precise prison made of magnetic and electric fields. The antimatter particles, which are electrically charged, are suspended in a perfect vacuum in the center of this trap, held away from all matter by these invisible force fields. It's like trying to hold a single hyperactive dust mote in midair using only a dozen carefully aimed hairdryers. It requires immense precision and constant flawless power. Any failure, any fluctuation, any tiny error, and your fuel supply instantly transforms into a bomb. Storing a gram of antimatter would be like holding a thermonuclear weapon. That could go off if the power ever flickered. The idea of keeping kilograms of it on a spacecraft is the stuff of heart attacks for engineers. So while the physics of an antimatter rocket is sound, the engineering and economics are, for now, pure fantasy. It represents a level of technological control over nature that we can barely imagine. It would require a civilization that has mastered energy production on a planetary scale, perhaps one that has built a Dyson swarm around the sun to power its antimatter factories. It is the fuel of a Type II civilization on the Kardashev scale, a species that has become the master of its solar system, not just a visitor. Yet it captures the imagination like nothing else. It is the ultimate fuel, the endpoint of propulsion technology. If we ever hear that a ship named Prometheus or Icarus is launching with an antimatter drive, we will know that humanity has truly come of age in the cosmos. We will have learned to bottle lightning, to harness the very fire of existence to push us into the great dark. It is a dream, a powerful, radiant dream of what we might one day become. Now, all these methods, nuclear, fusion, antimatter, rely on the same basic principle. You are carrying your fuel with you. This is the tyranny of the rocket equation, a cruel and unforgiving master for any spacecraft designer. It states that to go faster, you need more fuel. But more fuel makes your spacecraft heavier, which means you need even more fuel to push that heavier craft, which makes it heavier still, and so on. It leads to an exponential growth in the mass of your spacecraft. To get even a small probe to a nearby star in a reasonable time, you might need a fuel tank larger than the Empire State Building. It's a vicious cycle that seems to put star travel forever out of reach. So we need to think outside the box. What if we didn't carry our fuel? What if we could scoop it up as we go? This is the idea behind the Bussard ramjet, a brilliant concept proposed by physicist Robert Bussard in 1960. Imagine a starship with a gigantic electromagnetic scoop hundreds of kilometers wide on its front. As it moves through space, it scoops up the tiny stray atoms of hydrogen that float in the interstellar medium, only a few atoms per cubic centimeter. But if your scoop is big enough and you're going fast enough, you can collect a meaningful amount. This hydrogen would then be funneled into a fusion reactor, used as fuel, and blasted out the back for thrust. It's like a jet engine for space. The beauty is that you don't carry fuel. You become a self-sustaining engine. In theory, a ramjet could accelerate for years, eventually reaching relativistic speeds, a significant fraction of light speed. The problem? The interstellar medium is very, very thin. The scoop would have to be astronomically large to collect enough hydrogen, and the magnetic fields required would be immense. Furthermore, at high speeds, the collected hydrogen would be hitting the scoop like a torrent of cosmic radiation, creating huge drag and technical challenges. It's a beautiful idea, but one that may be more practical in the pages of a novel than in reality. Perhaps the most elegant and seemingly magical solution is to leave the engine behind altogether. This is the concept of the light sail. Instead of pushing yourself with expelled fuel, you let yourself be pushed by light. Photons, the particles of light, may have no mass, but they have momentum. When they bounce off a surface, they give it a tiny, tiny push. It's negligible on Earth, but in the frictionless vacuum of space, a constant push can lead to incredible speeds over time. We could build a gigantic, ultra-thin, and reflective sail, perhaps kilometers across. Then, we would point an incredibly powerful laser, or an array of lasers, from somewhere in the solar system, like orbiting the sun, at this sail. The constant pressure from this laser beam would push the sail, and the spacecraft attached to it, faster and faster. Since the laser beam doesn't diverge much, it could keep pushing the craft for a long, long way. Projects like Breakthrough Starshot are seriously investigating this for sending tiny, gram-weight probes to Alpha Centauri within a few decades. They would be pushed by a giant Earth-based laser to 20% the speed of light, arriving in about 20 years. For a crewed ship, the sail and the laser would need to be unimaginably larger, but the principle is sound. It's a beamed energy propulsion system, and it's one of the most promising concepts for fast interstellar travel. Okay, so let's assume we've cracked it. Through some miracle of future engineering, be it a compact fusion drive, a massive light sail, or a trickle of antimatter, we have built a starship capable of 10% of light speed. We name it the SS Ambition. We point it at Alpha Centauri, and we go. The journey itself, even at this fantastic speed, would take over 44 years. This introduces our next great challenge: time. Who goes on a 44-year journey? It's longer than most careers. You'd be saying goodbye to everyone and everything you ever knew on Earth, forever. This would have to be a one-way trip for colonization, or the crew would have to find a way to survive the 88-year round trip. This brings us to the concepts of generation ships, or hibernation. A generation ship is exactly what it sounds like: a gigantic, self-contained ark. It's not just a ship, it's a mobile world. It would have to contain entire ecosystems, farms for food, water, and air recycling systems, schools, hospitals, everything needed to sustain a human population for centuries. The crew that leaves Earth would not be the crew that arrives. Their children, or even their grandchildren, would be the ones to finally reach the destination. The social and psychological challenges are immense. Could a closed society remain stable and sane for generations in the empty blackness of space? Would they even remember or care about the mission their great-grandparents started? They might come to see the ship itself as their entire universe. It's a fascinating and terrifying prospect. The other option is to put the crew to sleep. Science fiction has made suspended animation or cryogenic hibernation a staple. The idea is to drastically lower the body's metabolism, slowing life to a near standstill, so that decades pass like moments for the sleeper. Bears hibernate. Some frogs can freeze solid and thaw out later. Could we do that to humans? We are a long, long way from that technology. The process of freezing creates ice crystals that shred cell membranes. We'd need to perfect some form of vitrification, turning tissues into a glass-like state without ice. Even if we could safely put someone under, keeping them stable and healthy for decades, and then safely reviving them, is a medical mountain we haven't even begun to climb. But it remains a compelling idea to circumvent the problem of time. There's another, even weirder aspect of time to consider when traveling at a significant fraction of light speed: time dilation. This is not science fiction. It's a proven cornerstone of Einstein's theory of relativity. The faster you move through space, the slower you move through time relative to someone who is stationary. Let's say our ship, the SS Ambition, is traveling to a star 10 light-years away at 90% the speed of light. For us on Earth, watching on a giant clock, the journey would take just over 11 years one way. But for the crew on the ship, because of their incredible speed, time would be passing more slowly. Their clocks, their heartbeats, their aging would all be slowed down. From their perspective, the trip might only take about 5 years. They would age 5 years while everyone on Earth aged 11. This effect becomes more extreme the closer you get to light speed. On a truly relativistic journey to the center of the galaxy and back, the crew might only age decades, while tens of thousands of years passed on Earth. They would return to a planet they no longer recognized. This solves the problem of crew longevity on long journeys, but it creates a profound existential loneliness. You are not just leaving your home, you are leaving your entire epoch. So, we've imagined ways to travel to another star, a monumental achievement to be sure, but that's just the first step. Our goal is to leave the galaxy. To do that, we need to understand the structure of our Milky Way. We don't live in a flat, featureless disk. Our galaxy is a barred spiral with major arms, Perseus, Sagittarius, Norma, Scutum Centaurus, and minor ones like our own Orion Spur. The Sun is located about 27,000 light-years from the supermassive black hole at the galactic center, Sagittarius A star. The disk of the galaxy is about 1,000 light-years thick on average, and we are roughly in the middle of that thickness. To leave the galaxy, we have two main choices: go up or down out of the galactic plane, or go outward through the disk towards the outer halo. The nearest edge of the galactic disk is, well, it's not a sharp edge. The density of stars just gradually decreases. But if we define the edge as where the star density drops off dramatically, we're talking about traveling from our position, roughly 27,000 light-years from the center, to maybe 50,000 or 60,000 light-years out. That's a journey of at least 23,000 light-years minimum just to get to the sparse outer fringe. Alternatively, we could try to go perpendicular to the disk. To get completely clear of the bulk of the galactic mass, we'd need to travel about 1,000 light-years up or down. Let's let that sink in. Our earlier heroic journey was to Alpha Centauri at 437 light-years. Now we're talking about distances of thousands of light-years. At our hopeful 10% of light speed, a 1,000 light-year journey up would take 10,000 years of ship time. And because of time dilation at that speed, it would still be 10,000 years for the crew. A journey to the outer edge, 23,000 light-years away, would take 230,000 years. These are not journeys. These are epochs. They span timescales longer than modern Homo sapiens has existed. This is why leaving the galaxy is in a completely different league of difficulty than merely visiting another star. The energy required for such a journey is beyond apocalyptic. It would require the total energy output of a star, harnessed and controlled by a civilization of gods. This brings us to the concept of the Kardashev scale, a way of measuring a civilization's technological advancement based on energy use. A Type 1 civilization can use all the energy available on its home planet. We are not quite there yet. We're about a Type 0.7. A Type 2 civilization can harness the entire energy output of its star, for example, by building a Dyson sphere, a megastructure encapsulating the sun to capture its light. A Type 3 civilization can control the energy of an entire galaxy. To even contemplate a mission to leave the galaxy, we would likely need to be a solid Type 2 civilization, masters of stellar energy. How would a Type 2 civilization approach this? Their ships wouldn't be the cramped vessels we imagine. They would be world ships, planetoids engineered for travel, or fleets of ships the size of continents. Their propulsion might not be rockets at all, but something even more exotic. Perhaps they would have mastered gravity control. If we could find a way to manipulate gravity to create a repulsive force against the fabric of space-time itself, we could potentially fall towards our destination without needing reaction mass. This is the idea behind the hypothetical warp drive of science fiction. While purely speculative, it's fun to explore within the bounds of theoretical physics. The closest thing to a warp drive in real physics comes from the work of Miguel Alcubierre in 1994. He proposed a mathematical model where a spacecraft could be enclosed in a warp bubble. In front of the bubble, space-time itself would be compressed. Behind the bubble, space-time would be expanded. The ship inside this bubble would itself be motionless in its local space. It's the space around it that is moving. This gets around the universal speed limit because the ship isn't moving through space faster than light. Space itself is moving around the ship. Think of it like a surfboard on a wave. The surfboard isn't moving through the water. The wave is carrying it. In this analogy, the wave is a distortion of space-time. The catch? To create this distortion, you need something with negative mass or negative energy density to twist space-time in the required way. Does such exotic matter exist? We have hints in quantum physics, like the Casimir effect, which shows negative energy densities can exist in a limited way. But the amounts needed for an Alcubierre drive are astronomical, perhaps requiring the mass energy of entire Jupiter-sized planets. It also has other nasty potential side effects, like building up a wall of high-energy particles at the front of the bubble that would vaporize your destination upon arrival. It's a fascinating thought experiment that shows us how space-time might be manipulated, but it is firmly in the realm of mathematical possibility, not engineering reality. Perhaps a more plausible, yet still incredibly far future technology for galactic travel would be the creation of a network of wormholes. A wormhole is a hypothetical tunnel through space-time, a shortcut connecting two distant points. You go in one end and pop out the other, maybe thousands of light years away. Again, the math and general relativity allows for such structures. But like the warp drive, they would require exotic matter to prop them open and prevent them from collapsing instantly. If a future civilization could stabilize wormholes, they could create a subway system for the galaxy. To leave the galaxy, you'd simply find a wormhole that had its other end out in the intergalactic void. But creating such a thing, or finding a natural one, is the stuff of cosmic fantasy for now. Let's assume we've become a Type 2 civilization. We've built a Dyson sphere around our sun, and we're harnessing nearly all of its energy output. We decide to build a vessel, an ark of arcs, to send a seed of humanity out of the Milky Way. What would the journey be like once we finally push away from the familiar spiral arms? The first thing we'd notice as we travel outward is the changing sky. The stars, which from Earth are a dense, glorious tapestry, would begin to thin out. The constellations would distort and melt away over the centuries. The Milky Way, that glorious river of light that has guided and inspired humans for all of history, would slowly shrink from a broad band into a faint, localized smudge behind us. We would watch our home galaxy recede, becoming just another island universe in the Black Sea. Ahead, there would be almost nothing. A few lonely, ancient stars of the galactic halo, and the faint, fuzzy blobs of other galaxies, trillions of kilometers away. The blackness would be deeper, more absolute than any human had ever experienced. The sense of isolation would be terrifying and profound. And what would we find out there, in the intergalactic void? It is not a complete vacuum. It contains a few atoms per cubic meter, compared to the few atoms per cubic centimeter in interstellar space. It is a desert compared to the ocean of the galaxy. There would also be dark matter, the mysterious, invisible stuff that makes up most of the galaxy's mass and extends far beyond the visible stars. We wouldn't be able to see it or feel it, but its gravitational pull would still be there. There might also be rogue planets, worlds flung from their star systems during cosmic collisions, now drifting forever in the darkness, frozen and dead. Perhaps our Ark ship could use one of these as a resource, mining it for water and minerals. The ultimate goal? Perhaps to reach another galaxy. The nearest major one is the Andromeda Galaxy, a beautiful spiral even larger than our own. It is 2.5 million light-years away. At 10% of light speed, the journey would take 25 million years. This is so far beyond human comprehension that it ceases to be a journey and becomes an act of biological destiny. The only way such a trip could be contemplated is with a completely self-sufficient world ship, with a society utterly dedicated to this single multi-million-year purpose, or with a crew in some form of perfect, eternal hibernation. Or, of course, with that mythical warp drive, making the trip perhaps manageable in a human lifetime from the crew's perspective. But here's a thrilling cosmic thought. We don't necessarily need to go to another galaxy. The Milky Way and Andromeda are on a collision course. In about 4 to 5 billion years, they will begin to merge into a new, larger galaxy, often called Milky Way. The dance will take billions of years. Stars are so far apart that actual collisions will be rare. The two galaxies will mostly pass through each other, their gravity pulling and twisting them into a new elliptical shape. So, in a way, if we just stay put, our distant descendants will witness a galactic merger. They will, in effect, experience a new galactic environment without ever having to leave home. But that's cheating for our question of leaving. As we push our thought experiment to its limits, we must confront the deepest questions of all. Why? Why would we ever attempt such a thing? The energy cost is unimaginable. The timescales are geological. The risks are infinite. The motivation would have to be equally powerful. Perhaps it is the ultimate insurance policy. Some cataclysm could make the galaxy uninhabitable. A wave of gamma-ray bursts from merging neutron stars, the awakening of the supermassive black hole at the center, or even the eventual death of all stars. Sending arcs out into the void would be a way to ensure that the spark of consciousness, the story of humanity, never completely dies. Or perhaps it is simply because it is there. The same insatiable curiosity that made us paddle across oceans, climb the highest peaks, and journey to the moon might, millions of years from now, compel us to see what lies beyond the shores of our galactic island. It is the final frontier, not just of space, but of time, energy, and life itself. So, can we leave our Milky Way galaxy? Today, with our chemical rockets and our fragile bodies, the answer is a gentle but certain no. It is a dream woven from the threads of distant possibility. But the universe is old, and we are young. We have barely taken our first steps. The laws of physics, as we understand them, do not explicitly forbid it. They just demand a price so high it seems mythical. They demand that we evolve, not just biologically, but technologically and as a civilization. They demand that we become masters of energy and time. They demand that we become, for all intents and purposes, a different kind of species altogether. The journey to the stars and beyond them is not a journey of distance. It is a journey of the mind. It is a test of our ingenuity, our patience, and our courage. It asks us if we can think in scales of centuries and millennia, not just fiscal quarters. It asks if we can cooperate as a planet to achieve a goal whose payoff none of us will ever see. The voyage out of the galaxy may never happen, but in asking the question, in daring to dream the blueprint, we are already stretching the boundaries of what it means to be human. We are reaching, once again, for the stars, and in doing so, we are reminding ourselves that the most powerful engine for any journey is not found in a reactor core, but in the boundless, hopeful, and curious human spirit. And that, perhaps, is the most important destination of all. Good night. Have a deep sleep.